All right, everyone, get ready for this. We are going deep into computer networks.
Ooh, computer networks sounds complicated.
Yeah, a little bit. But that's why we have you here to break it down for us, help us understand how all this stuff works, because I think most people use the internet every day, multiple times a day, but don't really have any idea what's happening behind the scenes.
I think you're absolutely right, and I'm happy to help you understand all the magic that happens when you send an email or you're streaming a video.
Yeah, like when I hit send on an email, how does it actually get to my friend on the other side of the world?
That's a great question, and it all starts with understanding how networks are structured, and a key concept is layering.
Layering. Okay. Is that like the different levels of a building or something?
It's a good way to think about it. Just like a building has different floors, networks are organized in layers.
Okay, so what are these layers and how do they work together?
There are two main models we use to describe network layering. There's the OSI model, which stands for Open Systems Interconnection. It's a theoretical model with 7 layers. But in the real world, we mostly use the TCP/IP model, which has 4 layers.
TCP/IP. Okay, so these models are like blueprints for how networks are built.
Exactly. They provide a framework for understanding how data is transmitted across networks.
So is TCP/IP the one that actually makes the internet work?
Yes, TCP/IP is the dominant model used in the internet today.
Okay, so TCP/IP is like the internet's operating system or something.
You could think of it that way. It's the set of rules that governs how data is transmitted and received across the internet.
Gotcha. So data is like the stuff we send, right? Like the emails and the videos and everything.
Exactly. Data is the information that's being transmitted over the network.
And it travels through these layers, right? But how does it actually physically move from one place to another?
That's where the physical layer comes in. This is the foundation of any network. It deals with the physical media that carry data, like cables and signals.
Cables. Ah, like the ones I see plugged into my computer.
Yes, those are part of it. The most common type of cable used in networks is called twisted pair cable. It's relatively inexpensive and easy to work with, but it has limitations in terms of speed and distance.
Okay, so for longer distances or faster speeds, we need something else.
Exactly. For those situations, we use fiber optic cables. They transmit data using pulses of light, and they're incredibly fast and can carry data over very long distances.
Wow, light. That's super cool. But what about Wi-Fi? That doesn't use any cables.
You're right. Wi-Fi uses radio waves to transmit data wirelessly.
So it's like having a little radio transmitter and receiver in my devices.
That's a good way to think about it. Wi-Fi is great for convenience and mobility, but it has limitations in terms of range and signal strength.
Yeah, I've definitely noticed that when my Wi-Fi signal gets weak.
Right, and another important concept related to data transmission is bandwidth.
Bandwidth? Is that like the size of the data pipe?
That's a good analogy. Bandwidth refers to the amount of data that can be transmitted over a network connection in a given amount of time.
So more bandwidth means faster speeds.
Exactly. A high bandwidth connection allows you to download and upload data much faster.
Okay, I'm starting to see the bigger picture here. We have data traveling over different physical media like cables and radio waves, and the speed is determined by the bandwidth. But how do we make sure the data gets to the right place and arrives in one piece?
That's where network architecture comes in. It's the overall design of the network and how different devices are connected and communicate with each other.
So it's like the roadmap of the network.
Exactly. And there are different ways to design a network. One important distinction is between circuit-switched and packet-switched networks.
Okay, those sound familiar. Is circuit-switched like the old telephone system where you had a dedicated line for your call?
Precisely. Circuit switching establishes a dedicated connection between 2 points for the duration of the communication. It's great for real-time applications like voice calls, but not very efficient for data transmission.
And packet switching is how the internet works, right?
Yes. Packet switching breaks data down into small units called packets and sends them independently across the network. Each packet has its own address information so it can find its way to the destination.
So it's like sending a letter, but cutting it up into pieces and putting each piece in a separate envelope.
That's a good visualization, and the packets can take different routes through the network and be reassembled at the destination.
That's pretty clever. But who's in charge of directing all this traffic, making sure the packets get to the right place?
That's the role of network devices, like hubs, switches, and routers.
Okay, so these are like the traffic cops of the network.
Yes, each device plays a specific role in managing data flow. Hubs are simple devices that broadcast data to all connected devices. Switches are smarter and can direct traffic to specific devices based on their MC addresses. And routers are the brains of the network, connecting different networks together and making routing decisions based on IP addresses.
RC addresses, IP addresses. I was trying to get lost in all these acronyms.
Don't worry, it's all part of the language of networking. A MAC address is a unique identifier for each device on a network, and an IP address is a unique identifier for a device on the internet.
So routers use IP addresses to figure out where to send data packets.
Exactly. Routers are like the postal service of the internet, making sure data gets delivered to the correct destination.
This is all fascinating, but we're just scratching the surface here, right?
Yes, there's much more to explore, but we'll save that for the next part of our deep dive.
Okay, I can't wait to hear more. This is already blowing my mind. Okay, so I think I'm starting to understand how the data gets around, but how do we make sure it arrives in one piece and doesn't get all garbled up?
That's a great question, and it's all about data transmission techniques and those protocols that we mentioned earlier.
Okay, so how do we make sure the ones and zeros that make up the data don't get flipped around?
Well, it starts with data encoding, which is like translating the data into a language that the network can understand.
So we're teaching the data how to speak network.
In a way, yes, we're representing the data as electrical or optical signals that can be transmitted over the physical media.
And there are different ways to do that, right? Like different encoding schemes.
Yes. There are many different encoding schemes, each with its own advantages and disadvantages.
Can you give us an example?
Sure. One common scheme is called NRZL, which stands for non-return to zero level. It's a simple scheme where a high voltage level represents a 1 and a low voltage level represents a 0.
Okay, but what if the signal gets distorted along the way? Like if there's interference or something?
That's a good point, and that's why we have other schemes like Manchester coding, which is less susceptible to errors because it introduces transitions in the signal to help synchronize the sender and receiver.
Transitions, so like little markers along the way.
Exactly. These transitions help the receiver to stay in sync with the sender, even if there's some noise on the line.
That's clever. But can things still go wrong even with these encoding schemes?
Yes, errors can still happen during transmission. That's why we have error detection and correction techniques.
Oh, so we have backup plans for when things go wrong.
Exactly. One simple method is a parity check, which adds an extra bit to each data unit to check for errors.
So it's like a little checksum at the end.
Yes, it's a basic way to detect single-bit errors, but for more robust error detection, we use techniques like cyclic redundancy check or CRC.
CRC, that sounds more intense.
It is. CRC uses a more complex algorithm to generate a checksum that can detect a wider range of errors.
So it's like a super detective for data errors.
You could say that CRC is very reliable at detecting errors, and it's widely used in networking.
That's good to know. So we've encoded our data and we're checking for errors, but how do we make sure everything arrives in the right order?
That's where framing comes in. It's the process of dividing the data into discrete units called frames, each with a header and a trailer.
A header and trailer like a book or a movie.
Exactly. The header contains information about the frame, like the source and destination addresses, and the trailer typically includes a checksum for error detection.
So framing is like putting each piece of the puzzle in a numbered envelope.
That's a great analogy. It ensures that the data arrives in the correct order and can be reassembled correctly at the destination.
Okay, so we've encoded the data, we're checking for errors, and we're framing it all up. What happens next?
Well, now we need to establish the rules of communication, and that's where protocols come in.
Protocols. I've heard of those, but I'm not really sure what they are.
Protocols are essentially sets of rules or procedures that govern how devices communicate with each other.
So they're like the language of the network.
Exactly. Protocols define the format of messages, the procedures for sending and receiving data, and how to handle errors.
So without protocols, it would be like trying to talk to someone who speaks a different language.
That's a good analogy. Protocols ensure that everyone is speaking the same language and following the same rules so that communication can happen smoothly.
Okay, so what are some of the key protocols that make the internet work?
One of the most important is TCP, which stands for Transmission Control Protocol. It's a connection-oriented protocol that provides reliable data delivery.
Connection-oriented, does that mean it establishes a dedicated connection between two devices?
Yes, like a phone call, TCP sets up a connection before transmitting data, and it ensures that all the data arrives at the destination in the correct order and without errors.
So TCP is like a guaranteed delivery service for data.
That's a good way to think about it. It's used for applications where reliability is crucial, like email and file transfer.
Okay, makes sense. What about UDP? I've heard that one mentioned before.
UDP, or User Datagram Protocol, is a connectionless protocol. It's faster and more efficient than TCP, but it doesn't guarantee delivery.
Connectionless, so it's more like sending a postcard. You hope it gets there, but you're not sure.
Yes, UDP is like sending a letter without a return address. It's faster, but there's no guarantee that it will arrive.
So it's a trade-off, speed versus reliability.
Exactly. UDP is often used for applications where speed is more important than reliability, like video streaming and online gaming.
Gotcha. So TCP is for reliable delivery, and UDP is for speed. And then there's IP, right? What does that one do?
IP, or Internet Protocol, is responsible for addressing and routing data packets across the Internet.
IP addresses. Those are like the street addresses for devices on the Internet.
Yes, every device on the Internet have a unique IP address, and IP is responsible for making sure that data packets get delivered to the correct destination.
So IP is like the postal service of the Internet.
Exactly. It's the glue that holds the Internet together, enabling billions of devices to communicate with each other.
Wow, it's amazing how all these protocols work together to make the Internet work.
It is. And there are many other protocols, each playing a specific role in the vast and intricate world of computer networks.
This is a lot to take in, but I'm really starting to understand how it all works. So what else is there to learn?
Well, we haven't even talked about wireless network security or emerging trends. Those are all exciting topics we'll explore in the next part of our deep dive.
Okay, so we've talked about all these wires and cables and protocols, but what about the wireless stuff like Wi-Fi? How does that work?
Wi-Fi, everyone's favorite invisible network.
Yeah, it's kind of like magic. You just connect and boom, you're online.
It does seem magical, but it's actually based on radio waves.
Radio waves, like the ones that play music on the radio.
Exactly.
Yeah.
Wi-Fi uses radio waves to transmit data wirelessly between devices.
So my laptop is like a little radio station.
In a sense, yes, your laptop has a Wi-Fi adapter that can send and receive radio signals.
Okay, so that's how I can connect to the internet without plugging in a cable. But what about when I'm out and about and using my phone? How does that work?
That's where cellular networks come in. They use a network of cell towers to provide wireless coverage over a wide area.
Cell towers, those big tall things I see everywhere.
Yes, each cell tower covers a certain geographic area called a cell. And as you move from one cell to another, your phone seamlessly hands off the connection to the next tower.
So that's how I can stay connected even when I'm driving.
Exactly. Cellular networks are designed to provide continuous connectivity as you move around.
And I've heard about 5G. Is that just like a faster version of cellular?
5G is the next generation of cellular technology, and it promises much faster speeds, lower latency, and the ability to connect many more devices.
So it's like a supercharged cellular network.
Yes, 5G has the potential to revolutionize the way we use mobile devices and enable a whole new range of applications.
That sounds exciting. But what about places where there's no cell service, like out in the wilderness or something? Is there any way to connect to the internet in those situations?
Yes, for those cases, we have satellite communication satellites orbiting the Earth can beam internet signals to even the most remote locations.
Wow, so I could be in the middle of nowhere and still be online.
Exactly. Satellite internet is a great option for people in remote areas or for situations where terrestrial internet infrastructure is unavailable.
That's pretty amazing, but with all this connectivity comes the issue of security, right? How do we keep our data safe from hackers and cybercriminals?
That's a crucial question. Network security is essential for protecting our data and privacy.
So what are some of the ways we can protect ourselves?
Well, one important measure is to use a firewall. A firewall acts as a barrier between your network and the outside world, blocking unauthorized access attempts.
So it's like a security guard for my computer.
Yes, a firewall can help to prevent hackers from getting into your network and stealing your data.
Okay, that's good to know. But what about when I'm sending sensitive information over the internet, like my credit card number or something? How do I make sure that stays private?
For that, you need encryption. Encryption scrambles your data so that it's unreadable to anyone who doesn't have the key to decrypt it.
So it's like putting my data in a secret code.
Exactly. Encryption is essential for protecting sensitive information online.
And what about VPNs? I've heard those are good for security too.
Yes, a VPN, or virtual private network, creates a secure encrypted tunnel between your device and the internet.
So it's like having a private line.
In a way, yes, a VPN encrypts your traffic and hides your IP address, making it much harder for anyone to track your online activity.
Okay, so firewalls, encryption, VPNs, those are all important for staying safe online.
Absolutely, and it's important to stay informed about the latest security threats and best practices for protecting your data.
So what's next for computer networks? What's the future hold?
The future of networking is full of exciting possibilities. One major trend is software-defined networking, or SDN, which is making networks more flexible and programmable.
So we're moving away from hardware and towards software.
Yes, SDN allows us to control and manage networks using software, which makes them much more adaptable and scalable.
That sounds pretty powerful. What else is on the horizon?
Another big trend is network virtualization, which allows us to create multiple virtual networks on top of a single physical network.
So it's like having many networks in one.
Exactly. Network virtualization allows us to share resources more efficiently and reduce costs.
This is also fascinating. It's incredible to think about how far computer networks have come and where they're headed.
It is, and it's all thanks to the brilliant minds who have worked tirelessly to connect the world and make information accessible to everyone.
Well, I've learned so much today. Thank you for taking us on this deep dive into the world of computer networks.
It's been my pleasure. And to our listeners, thank you for joining us on this journey into the fascinating world of computer networks. We hope you've enjoyed the ride.